Chapter 28. Once again, this is now our review, so we've learned about the chi-squared goodness of fit test and the chi-square test of independence. Now we're going to put them together and look at different problems and try and figure out which test we need to use for which. So a computer is designed to generate A, B, C, and D at random. In 1,000 tries, we get 271 A's, 237 B's, 235 C's, and 257 D's. So looking at my table, this first column must be my observed, since that's my actual data. Now you have to decide which chi-square test this is. One of the really easy ways to think about it is, does it have two different variables that might be interacting? In this case, no, there's not two different variables. It's not something like gender and handedness, or vaccines and whether or not you get the flu. We only have one variable, which letter you get. And so just by that, it has to be the chi-square test for goodness of fit. Now we wanted to conduct a test to see if the letters are generated at random. If they're generated at random, that means they should all be equally likely. So with 4 letters, that's like saying if they're all equally likely, then each percentage or each chance should be 25%. And so it's like saying, or asking this question of is it random, is like saying, okay, were each of these chances really 25%? Or were each of the percentages 25%? So to do that, let's find our expected values. If each one was supposed to be 25%, it would be 25% over 100 times our total of 1,000. Since that's how you figure out your expected, that's your percentage times your sample size. And this would give us 250. So we expect 250 each time. Now we didn't get 250 for each letter, but now we're wondering, are those slight differences just the natural chance error, or is there something big going on? Maybe the computer is making a mistake, and that's why we're getting such big differences. Let's see. So we already said it's the chi-squared goodness of fit. And you should always check if you can do the test. So as the check, make sure all expected frequencies are at least 5. So check them, they're all 250, so we're good there, so we can do the test. Now let's come up with our hypotheses. The null hypothesis would be that the letters are random, or you can think of it as the chance for each letter is 25%, that they would all be equally likely. The alternative would be then that they are not random, or not all the chances are 25%. Now when we say that they're not all 25%, maybe just one is off, although people that are paying attention tell me, well, it has to be at least 2 that are off, because if one is low, one would have to be high, since they all have to add up to 100%. So maybe 2 are off, maybe 3 are off, maybe all 4 are off. We don't really know, but just that they're not all 25%. Now for our test statistic, chi-squared. Once again, we're lucky because the chi-squared test statistic is the same for both tests. So chi-squared is going to be the sum of each observed minus expected squared over the expected. So in our case, our first observed is 271 and the expected is 250. Squared over 250. Plus my next one is 237 with an expected of 250. And 235 observed, 250 expected. And 257 observed, 250 expected. So chi-squared equals 3.536. Now let's find our degrees of freedom, which in this case is just your number of categories minus 1. So when we look at it, we have 1, 2, 3, 4 categories, so 3 degrees of freedom. Here is my chi-squared equals 3.536. We want the area to the right with 3 degrees of freedom. So we have 3 degrees of freedom. We're looking for the number of 3.536. That'd be in between these two values, so my p-value is between 30 and 50%. So my p-value is between 30% and 50%. So, this is a big p-value, so we fail to reject the null hypothesis. Now once again, all of your conclusions are always written in terms of the alternative, which was that the letters were not generated at random, so we don't have enough evidence to say that the numbers aren't generated randomly. We still don't know for sure, but we don't really have any reason at the moment to think that they aren't random. So, no reason to think the letters aren't all equally likely. Now this question down here, I wanted to know, does the test tell you, our chi-square test tell you which category is most likely or least likely? Well, in our case, it doesn't matter here since we said no reason to think they aren't equally likely. But if we had gotten a different result, the test doesn't say which chances are bigger or smaller, just that they aren't all 25%. Let's try our next example. A simple random sample of 200 Utah students are asked whether or not they like math. 102 are boys, of whom 41 like math. The other 98 are girls, of whom 29 like math. And we want to know, is liking math independent of gender for Utah school children? Well, right away it says the word independent, so I know I'm probably going to want to use the chi-square test for independence. Also, notice we have two different variables, whether or not they like math and which gender they are. So two different variables, so it has to be the chi-square test of independence. Now for our chi-square test of independence, let's start off by finding our expected frequencies. Remember, it takes a little while to find them for the chi-square test of independence because for each one you have to do row total times column total over the grand total. So let's go ahead and do it. Let's do boy and like math. So for boys and like math, that would be 102 times 70 over 200, because my row total was 102, my column was 70, and the grand total was 200. So this is 35.7. Now on this one I didn't give you another table because I actually find it easier to leave a little extra space and just write in the 35.7, and since that one's handwritten, I know all of the handwritten values are expected. And then let's do girls and don't like math. So that has a row total of 98, a column total of 130, so times 130 and divide by my grand total of 200. So this gives me 63.7. And I can tell you I already figured out the other two. There's 66.3 and 34.3. Now one thing to keep in mind is if you add up these expected values, so 35.7 and 34.3, you will get 70. And if you add up 66.3 and 63.7, you're going to get 130. Sometimes you'll be just a little bit off due to rounding, but that's not a big deal or the important thing here. And if you do 35.7 and 66.3, you're going to get 102 and 98 and 200. So just as a little side note, to double check your work, the totals for the observed and expected should match. That's just a way to double check your work. Okay, let's see. So we found all our expected. Let's go ahead and check. Are all expected frequencies at least 5? So it looks like my smallest one is 34.3. So we are good there. We can go ahead and do this test. The null hypothesis is always that your two variables are independent so that they do not affect each other. So gender and liking math are independent. They do not affect each other. And the alternative would be that gender and liking math are dependent. So they do affect each other. Let's find our test statistic, chi-squared. Once again, it's just the sum of each observed minus expected squared over the expected. So my first observed is 41 and the expected is 35.7 squared over 35.7, and my next observed is 61 and its expected is 66.3 squared over 66.3, and 34.3, oh nope, sorry, wrong one. My next observed is 29 with an expected of 34.3. And finally, 69 minus 63.7 squared over 63.7. So I've done each observed minus expected, squared it, and then divided by the expected. So my chi-squared is 2.47. And your degrees of freedom are your number of rows minus 1 times number of columns minus 1. So that's one of the big differences between the two tests, is your degrees of freedom are different. So come back up, don't count your totals or headings, so we just have 2 rows, 2 columns. So with 2 rows, 2 minus 1, 2 columns, so we get 1 degree of freedom. So to find my p-value, here's chi-squared equals 2.47. We want that area to the right with 1 degree of freedom. So 1 degree of freedom, we're looking for the number 2.47, so that would be in between 1.07 and 2.71. So my p-value is between 10 and 30%. So once again, 10% and 30% was what I said. So this is a big p-value. So we fail to reject the null. So we didn't find enough evidence to conclude that gender and liking math are dependent. Or in other words, no reason to think that gender and liking math affect each other. Now in this situation, it would have been obvious that gender would have been affecting your liking math. If you suddenly decide to like math, your gender is not going to change. Now, does this test tell you whether boys or girls are more likely to like math? Well, to start with, the chi-square test itself doesn't tell you which gender is more likely to like math, even if they were dependent, which they weren't. And since they are not dependent, boys and girls should be equally likely to like math, since the variables don't affect each other. In this example, we're talking about the game of chess, in which the first few moves are important, and there's 5 different strategies that are highly favored by chess experts. To determine whether one or more of the strategies is most preferred by the grandmasters, a random sample of 100 grandmasters is taken, and each is asked which of the strategies he or she would prefer to employ. And so here are the responses. So you have 5 different strategies, and here are the observed frequencies. So 17 of the masters liked A, 27 liked B, etc. So that's our observed values. And we want to make a chi-square test of the null hypothesis that there's no difference in preference of strategy by the grandmasters. Okay, notice once again here, it doesn't seem like there's 2 different variables that we're wondering if they affect each other. Instead, to me, it seems like they're asking, are these strategies equally likely? And so this would be a chi-square test of goodness of fit. Because we're wondering if they're equally likely, are all the percentages 20%? %, because there's 5 of them. 100 divided by 5 is 20. And so if we expect 20%, then how do we find these expected frequencies? So the expected is going to be 20 over 100, since it's a percentage, times our grand total of 100, or 20. If they're equally likely, then it's just 100 divided by 5. They should each be 20. Now notice we're obviously not getting exactly 20, but is that just our natural chance error, or is there some underlying preference here? One of the things we should always do is check, are all of your expected frequencies at least 5? Well, the smallest is 20 since they're all 20, so yes, we're good there. We can go ahead and do this test. Now for your null hypothesis, that would be that the strategies are all equally likely, and the alternative is that the strategies are not all equally likely. Now this won't tell us which one is most likely or which one is least or which ones are most. It would just tell us that they're not all equally likely. So for my test statistic, chi-squared is equal to the sum of each observed minus expected squared over the expected. So in our case, our first observed is 17 minus expected of 20 over 20. And our next observed is 27 minus expected of 20 over 20. And 22 minus 20 squared over 20. And 15 minus 20 squared over 20. And 19 minus 20 squared over 20. So we get 4.4. Now for your degrees of freedom, for the chi-square test frequency of fit, it's number of categories minus 1. So we have 5 categories minus 1 gives us 4. So here's my chi-squared equals 4.4. We're looking for the area to the right. We have 4 degrees of freedom. Now in our last 2 problems, our degrees of freedom and our test statistics have been pretty similar. That's just pure coincidence. So 4 degrees of freedom, we're looking for 4.4. That's in between 3.36 and 4.48. So my area is between 30 and 50%. It's also a coincidence that all the problems we've done in this video have had big p-values. So the p-value is between 30% and 50%. So that is a big p-value. So we will fail to reject the null hypothesis. So we didn't find enough evidence to conclude that the strategies aren't equally likely to be chosen. So no reason to think that they're not all equally likely. And our last problem, use the data in the table to carry out a test of the null hypothesis, which is belief in the afterlife is independent of race. So obviously this one would be a chi-square test of independence. Because it's telling us, is belief in afterlife independent? So it's, just putting it right out there for you, is belief in afterlife independent of race? It would have to be a chi-square test of independence of fit. There, chi-square test of independence. Let's see. So the data's here, so this would have to be my observed in this table. And then the second table must be where I need to put my expected values. Let's go ahead and find our expected frequencies. Our expected frequencies is going to be our row total times our column total divided by our grand total. So let's do the spot first. Oh, look, they didn't give me any totals, so I need to go ahead and find the totals. So 621 plus 239 gives me 860, and 89 plus 42 gives me 131. And if I add those two together, I should get 991. Now let's find our column total. So 621 and 89 gives me 710, and 239 and 42 gives me 281. Okay, so now with that, let's say I want to find it for yes and white. So for yes and white, that's 860 and 710 over our grand total of 991. So this is going to give me 616. And I think because all of these numbers are so big, I just kind of rounded to the whole number. And let's do maybe black and no. So black and no, that's 131 for row total and 281 for column total, divided by my grand total of 991. This gives me 37. So here's my 37, and I'm going to go ahead and tell you that the others are 244 and 94. Now let's double check that all of our totals match up. So 616 plus 244 does give me 860. 94 and 37 gives me 131. 616 and 94 give me 710. 281 and 991. Just remember, double check your work. Your total should match up for both the observed and expected, and they do, so that's a good sign. Okay, now before we do the test, let's check are all observed, not all observed, all expected frequencies at least 5. So yes, the smallest one is 37, so we're good there. So we can go ahead and do this test. If you ever came across a situation where one of your expected frequencies was smaller than 5, what you'd say is, I can't do this test, and instead you could go use what we call a non-parametric test, and in this case you could use, it's called Fisher's exact test. But it is very long and complicated to do, and even a computer gets slowed down if your table is very big. So the null would be that belief and race are independent, that they do not affect each other. And the alternative is that belief and race are dependent, so they do affect each other. And my test statistic, chi-squared is equal to the sum of each observed minus expected squared over expected. So my first observed is 621 with an expected of 616. And then 239 and 244. $89 and 94, and 42 and 37. When I put all this together, I should get 1.08. My degrees of freedom is 2 minus 1 and 2 minus 1. Sorry, I should write down the formula, huh? So number of rows minus 1 times number of columns minus 1. So let's go back up. We have 2 rows and 2 columns because we don't count our totals or headings. So 2 rows, 2 columns. So this gives me 1 degree of freedom. So here's my chi-squared equals 1.08. We want that area to the right. With 1 degree freedom. So 1 degree freedom, we're looking for 1.08. So that is in here. So we're between 10 and 30%. So p-value is between 10% and 30%. So that is a big p-value. And once again, it's just a coincidence that all the p-values in this movie have been big p-values. So we failed to reject the null hypothesis. And so we didn't find enough evidence to conclude that race and belief in afterlife affect each other. Now this would be another one where it's obvious which one would be affecting which. Obviously race would have to affect your belief in afterlife. You're not changing your race based on your belief. But in this case they're not affecting each other, so it doesn't really matter. You could also think of it as we are sticking with the status quo. So we didn't reject it. We didn't find enough evidence. We're not concluding anything new, so we're kind of sticking with the status quo that they don't affect each other. Now there is a note here that unfortunately all we can say based on this hypothesis test is whether or not race affects belief in afterlife. We couldn't actually say which race is more likely to believe in an afterlife. Now this doesn't matter in this situation because they don't affect each other anyways. So not important here since they don't affect each other anyways.